to get a complete picture of the sun, we have to go to eclipses.
I don't think everybody understands how complicated the physics behind this type of object really is.
They thought it was an act of the gods and that it might be the end of the world.
It'll be a game changer.
Easter Island, what a great place for an eclipse.
This looks very interesting. Okay, this is it. I think we finally found the place.
When you look in detail at the sun, you can see that it's filled with very dynamic and very large events. And understanding these things and how those changes affect us here on the Earth is something that we're still barely being able to do.
What you've got going on in the core of the sun are millions and millions of hydrogen bombs going off per second, compressed and held in by the gravity of the sun.
This storm came around and produced some of the most intense electromagnetic disturbances in the space environment of the Earth that we've seen for a really, really long time.
Space weather is a field that didn't exist 15 years ago. And now it's spread across several government agencies, and we're getting funding to do the research to try to understand it and be able to predict it.
We've got some great spacecraft to study the sun. We've got some great mountaintop observatories to study the sun. But there are still many things that we learn at eclipses that we can't learn at other times. To get a complete picture of the sun, we have to go to eclipses.
A solar eclipse occurs when the moon happens to get in the right spot between the sun and the earth, casting a shadow on the earth. So the earth is basically moving through the moon's shadow, and that's what a solar eclipse is. This ratio of 400 times larger to the 400 times closer creates a perfect situation where the moon completely blocks out the solar surface and allows us on Earth to see a total solar eclipse. We're the only planet in the solar system that experiences total solar eclipses, and it's just a really neat coincidence that this distance and size ratio exists.
The sun's a great big ball of gas, a million miles across, and we see that hot everyday surface giving us a lot of light. But that's just a fuzzy atmosphere. It just happens to look sharp because we can't see the edge in such detail. But there's a whole region just around the everyday sun that we can see best at eclipses.
Think of looking at the sun like looking into the high beam of a car coming at you at night. It's so bright that details are washed out and you can't see anything. Now, take that light away, and new details emerge that you couldn't see before. In the case of a solar eclipse, now we can see that the sun has an atmosphere, just like here on Earth, the corona. And it's here that we think that space weather might begin. Well, it seems natural that during the time of the eclipse, anyone standing on a side of the Earth facing the sun should be able to see the eclipse. But that's not how it works. There are actually two shadows that the moon casts upon the Earth. This first one, it's very large and very diffuse, thousands of miles in size, is the penumbral shadow. Inside of the penumbral shadow, an observer can only expect to see a partial eclipse of the sun. The moon doesn't completely block out the sun. But here, in this much smaller, much darker shadow, the umbral shadow, no more than a couple of 100 miles in size, the moon completely blocks out the sun, and here you can expect to see a total eclipse.
The length of that path might be 10 or 12,000 miles long, but it's very narrow and it only covers a small fraction of 1% of the Earth's surface.
So when we're preparing to observe an eclipse, we look on a map and we see where that path is going to cover, where we have to be within the path. It turns out that the only substantial land it goes over is Easter Island. And other than that, it's going over Pacific Ocean.
They didn't know the mechanics that this was a natural phenomenon. They thought it was an act of the gods and that it might be the end of the world.
We're going to be ready, but we're dependent on all the equipment functioning, on the weather being good. If something goes wrong, then we'll have to wait another couple of years for the next total solar eclipse.
The energy output of the sun is hard to imagine, but if we stop for a second and consider the amount of energy that man has produced over the past 5 or 10,000 years, the sun produces 1 million times more energy every second.
That corona doesn't just stop at some hard boundary, it actually streams outward. The entire solar system is permeated by this ever outflowing, constantly dynamically changing wind.
And this wind blows past all the planets, the asteroids, all the way to the very edge of the solar system.
If you're sitting in front of a stove and you're too hot, you move away and it gets cooler. Well, if you're at the solar photosphere, the everyday surface of the sun, and you move away, you move outward into the chromosphere corona, it gets hotter. So that seems odd offhand, and so why is that?
It's doing something that we don't quite understand. It's transporting energy from the cold part to the hot part.
In fact, the distance from which it goes from about 10,000 degrees to this 1,000,000 degree is only on the order of like 50 miles.
The problem has been solved. It's been solved a dozen times over, and there are a dozen different answers. So, of course, that means it really hasn't been solved, and we want to choose among those different solutions.
We are studying the inner solar corona using the large spectrograph, which is possible only during the total solar eclipses.
There was a total eclipse that passed through Europe in 1842, and that was the first time in centuries that any European scientist had had a chance to see a total eclipse. They were totally amazed at the corona. They didn't know anything about the corona, so here was a new mystery to try to uncover.
Spectroscopy allows us to take light from a faraway source and compare it to standards here on Earth to figure out what something's made out of. If we know that sodium burns with a certain color and we see that same color coming from a foreign object, in this case the sun, we can be positive that that sodium is present there. We can even infer by their intensities how much of those elements are present.
This new element that was discovered was given a name helium for the sun, Helios.
Fusion is a nuclear reaction which produces energy. It's when light atomic nuclei, usually isotopes of hydrogen, combine to form heavier atomic nuclei, and energy is released in the process.
Three, two, one. Entering pulse.
It only lasts 2 seconds. But during those 2 seconds, we're pumping the power demand of an entire city into a small chamber a few meters in diameter. It's really an amazing thing that happens here every 20 minutes. We really believe that we can have a major impact on the future energy balance of the world, and if we are successful, it'll be a game changer.
The telescope looks at a very specific wavelength of light. The sun, of course, is made up mainly of hydrogen and helium. And as you start to tune the filter of the telescope to the correct line, which is the hydrogen line, you'll actually start to see features appearing coming out of the sun. This is the area of the sun where you actually see the cause and effect of what all the other layers of the sun underneath are doing. There's been very little information done about what you can actually see through a hydrogen alpha filter during an eclipse. So yeah, we get to see probably some very exciting phenomenon occurring once that starts to happen.
These are bright red clouds of hydrogen gas in close to the surface of the sun, and they extend out beyond the edge of the moon as these red tongues of fire.
volcano analogy is a pretty good one. They'll develop and they might sit for a day or a week, and then all of a sudden they get in a bad mood and they erupt. And you wonder, why did they decide to erupt now? What's the straw that breaks the camel's back?
The sun is a huge ball of very, very hot gas, and it's not solid like the Earth, and so it will actually rotate at different speeds depending on where it is on the surface and inside the sun. So it's all this gas that's basically rotating at different speeds. And I don't think everybody understands how complicated the physics behind this type of object really is.
A dynamo means some mechanism for converting mechanical motion into electricity. So it is believed that there's something moving around in the sun, and that's making electricity in effect, and that electricity is making magnetic fields. They writhe, they twist up, they get bigger, they explode, they merge with each other, they do all sorts of crazy things. There's a lot of complexity.
A magnetized plasma has a very organized, magnetically organized way of behaving. That's why when you look on the surface of the sun at these beautiful NASA images, you'll see these archways of plasma. What's happening is you've got a magnetic loop that is bubbling through the surface of the sun. Then the plasma that makes up the sun has an easy time filling up this loop, but then it's trapped. It's magnetically confined, as we say. One way to picture it is that the magnetic field lines are kind of like rubber bands, and you stretch them only so long and then they snap. But when they snap, they instantly reconnect into another reconfiguration.
space weather storms set up currents in the upper part of the Earth's atmosphere called the ionosphere. Those currents are reflected underneath in the solid Earth, and they feed into the power grid at the transformers.
The power, the sheer power, there are tens of billions of watts of power dumped in these auroral events.
Since grids today are all connected, this can cause kind of a progressive failure that could propagate across the country. In the most severe case, you lose distribution of goods and food and the purification of water. These are all the worst scenarios that could happen.
A solar storm can actually produce catastrophic effect on this planet, which can be about 20 times more economic damage than the Hurricane Katrina produced.
Couldn't be better. Look at that. Sky clear from there to there.
That's kind of the way nature works in cycles. It goes from maximum to minimum. It's pretty regular, but there are times when it does things we don't expect.
Earth is on a very delicate balance with the energy budget that we receive from the sun. Any small fluctuations will have important ramifications for life here on Earth. In one case, it could produce ice ages. In another case, it could produce drought and even evaporate the seas.
So the whole sun is very quiet, the corona is very quiet, it's melting away to some extent. We've seen the extent of the corona diminish from the 2006 eclipse we observed in Greece to the 2008 eclipse we observed in Siberia to the 2009 eclipse we observed in China, and probably it will be even more diminished in the 2010 eclipse on Easter Island. We haven't seen anything like this in at least 100 years. So it's getting to a very interesting, maybe even worrisome situation.
At some point, if the sun really, really changes its activity level, we're talking about survival of our species at the level we would like to maintain.
And then you can compare that to eclipses taking place in other years in the past and see if the sun's diameter has changed between these different eclipses. When Einstein came up with his theory of relativity, he realized that one way to test it was during an eclipse.
And Einstein's theory predicted how much those stars should shift in a photographic plate, and it turns out he was exactly correct. From an everyday standpoint, things like GPS absolutely would not work if you did not include the effects of relativity. The whole GPS system would be worthless if you didn't have relativity. It's a shock even to people in the 21st century. I've seen an eclipse, I knew exactly what was going to happen, when it was going to happen, down to the second, and I was still blown away when it actually happened.
The lighting during an eclipse is different than any other natural circumstance or unnatural circumstance. The horizon looks like dawn or dusk, but 360 degrees around.
I've seen cows heading back to the barn as though it were evening. Flowers begin to close up as though it were night. Sometimes bats might start coming out the last few minutes before totality.
One of the most interesting effects that happens during the partial phases of a total eclipse, that is, things which are very ordinary, like a shadow from this plant, start to become very extraordinary. So what I've done is I've set up a 5,000 watt light to act as my sun, and I've created a disk which will act as my moon. So right now the sun is doing what it normally does. The light is shining onto this plant, and we see very ordinary shadows as we would normally expect. as the eclipse starts to happen, things change. And now I can see little eclipse suns on the ground. This is because light coming from my sun is trying to make its way through the plant. The leaves are blocking most of it, but the patterns of the leaves in the plant start to form tiny little spaces, pinhole cameras. And due to the physics of the way light works, these little pinholes will focus the light and make actual focused images of the sun. And I can exaggerate that using my hand, and the spaces between my fingers will act as their own pinhole cameras, as if there are more leaves and a small breeze blowing, and those images will start to dance around on the ground. And it becomes a very incredible effect.
It really is very awe-inspiring to see it get dark in the middle of the day. The partial part of the eclipse takes an hour and a half or so. It gets gradually darker, but the last 15 minutes or so, you really see that the light is strange, the shadows get very eerily sharp, and then the last 15 seconds or so, it gets about 1,000,000 times darker. When you look up, you see this diamond ring in the sky, a bright bead of sunlight. All of a sudden it gets 1,000,000 times brighter. To see it get 1,000,000 times darker and then 1,000,000 times brighter within a few seconds is just a fabulous thing.
Now this diamond is going to break up in a few seconds into a series of beads as sunlight shines down the narrow valleys along the moon's edge.
It'll look reddish around the edge of the sun. That'll be the chromosphere, a thin layer of the outer solar atmosphere. Then that'll get covered after a few seconds, and you see the corona for the duration of the eclipse. You can do a lot in 4 minutes. You can take a lot of photographs, you can take a lot of looks, and then all too soon you get these phenomena in reverse. The partial eclipse will still last another hour and a half, but it's been said that nobody ever saw the end of this partial eclipse because you're so excited.
Everything's working.
incredible thing I've ever seen. It's nothing like the pictures. And you can, there's so many things you don't even realize until you actually see it.
Oh, that's just fabulous. We then take the data back to Williams College and work on our computers for months or years to straighten things out.
If we can study one star in really great detail and learn what makes it tick, then we have the key to understanding essentially the rest of the universe. So we can look at stars that are really far away and they're a pinpoint of light, and okay, you can get a lot of information, and astronomers have done an amazing job, but there's really no substitute for being able to look up close at this amazing star.
You really need to probe out there that can actually touch, smell, taste the sun. That's what these sensors on solar probe will do. They will actually measure the particles, their velocity, their density, their magnetic field. I mean, how exciting is that?